Hello folks, today we're going to be looking at an introduction to visual sensing and perception, and we're going to be starting to look at a different book, Computer Vision Algorithms and Applications, chapters 2.1 and 12.2. So there's lots of different types of sensors that are used in robotics, including proprioceptive sensing, which is to sense the robot's own body position, inertial sensing, which senses the acceleration of some link on the robot, visual sensing, which uses some sort of light, either visible light or some other spectrum of light, to sense the 3D scene. And then there's also tactile sensing, which we'll be looking at in a future lecture, as well as other types of sensors that may be useful for different applications. In general, regardless of what type of perception we're going to be looking at, there's a general sort of perception pipeline. First, we're going to want to produce some sort of mathematical model relating the raw sensor data to the quantities of interest underlying that physical phenomenon. These models can either be from mathematical or physical first principles, or they could also be data-driven, relating some sort of ground truth to sensor data, or some sort of combination of the two. The second things that we want to do is then to estimate the quantities of interest using that model. And there's lots of different ways that people have done this in the past, ranging from optimization to machine learning algorithms. And if we are really smart about doing perception, we may want to also self-supervise our perception models to perhaps improve our models to for example, deal with the changing distribution problem, basically changing conditions. Now, to do well in perception, we have to devise accurate models. We have to gather data to train those models or to estimate those models accurately, and also to develop computationally efficient algorithms for doing this estimation process, step 2. Now, there's a bit of a subtle point here. I've used the words sensing and perception, and at first glance, they seem like somewhat like synonyms. Now, in this class, we're going to distinguish sensing versus perception as follows. Sensing is going to be the act of acquisition of signals from hardware. So essentially the way in which the signals are actually generated. Perception is the second step, which processes those raw signals into some sort of representations that are meaningful to downstream tasks. So as an example, if we're trying to recognize digits from some sort of scan, the pixels themselves will be the sensing part, so gathering the camera images. But then detecting which digit that image represents is going to be the perception task. So there's different levels of perception in terms of different levels of sophistication of what is being produced for that downstream task. So for example, if we're trying to detect humans, detecting a blob of pixels with skin color is perhaps one form of perception, which is fairly low level, versus detecting a face, which is higher level, versus detecting whose face and what they're doing, which may be a much higher level input to some sort of planning algorithm. So near the lower levels of perception, the line is somewhat blurred, and so you can sort of discuss sensing tasks as essentially being low-level perception tasks. But in any case, certainly at the higher levels of object recognition and so on, we're talking about perception. So the general way that we can think about sensing and perception is that the top few blocks here are involving sensing. So there's some sort of physical phenomenon of interest, as well as potentially confounding factors driving the physics of some sort of acquisition device, the actual sensor. So there's going to be a physical transmission to get those signals into some data acquisition device, which is going to be digital. And then that is going to be then input into our decision-making system, our robot's mind, if you will. So this is all essentially part of the sensing pipeline. Then after this data gets into our computer, we're going to be able to use some sort of model of this the signal formation, a model of these confounding factors, and we're going to try to invert essentially the process that was given in the top half of this figure to try to estimate that underlying physical phenomenon. So in any case, these blocks here are basically the sensing component, and then these blocks here are the perception component. So another way that you can think about this is that the first half of this diagram is some sort of forward transform, which is producing our sensor data Z from the underlying phenomena of interest X, as well as some of these confounding factors epsilon. There's some forward transform G that we would like to then invert. so that given z, we can now estimate x. There's a couple of approaches for this. We could either try to model the g and the epsilon from physics or experiments and then somehow invert this. So basically using our own intuition and analysis, be able to construct this g function. And we'll look at some of these models that are used with this approach today. Another approach we'll be looking at much more in the future will be to try to model this function f directly through experiments. So if we have the ground truth x, and we have the ground truth of z, try to just estimate f directly. Now, there's lots of different types of perception tests that fall into this framework. So in, for example, ECE classes, you'll be learning a lot about signal filtering, state estimation, etc. We'll be looking a bit at 3D perception, in particular 6D object pose recognition and some segmentation as well. Now, with computer vision, we don't really think about 3D objects, but we think about images that represent 3D objects. And so, for example, object identification and segmentation and tracking and so on are tasks that we'll look at with computer vision. In other robotics tasks, you'll look at, for example, inertial perception or audio perception, which we won't look at in this course, but we'll talk about tactile perception using force torque sensors in a later class. Okay, let's start talking about visual perception. So these types of sensors, which are extremely rich and also very low cost, include visible light cameras, depth sensors, and laser sensors. We'll want to do things like perform stereo reconstruction of a 3D world. We might want to recognize objects, perform 3D mapping, also recognize objects that we've seen before and where they exist in our scene. And we may also want to understand how our robot is interacting with those objects. So the key issues that we'll talk about today and also subsequent lectures include how do we model cameras, and how do we then apply these models to estimate quantities of interest. How do we then fit the models in the presence of noise and errors, which will be the topic of next class in calibration. And we're also going to talk about representation of 3D models as well. So various types of sensors that are quite inexpensive and available, essentially off the shelf, include visible light cameras, which will give you an image, of course, at usually 30 frames per second or 60 frames per second. And there's also stereo cameras, which give you a pair of these visible light images. There's also depth field sensors, which try to give you an image of depth, basically distance to the camera, but it's slightly different than distance. We'll talk about that subtlety in just a few slides. But in any case, there's two major types of such cameras. There's structured light projection, as well as time of flight, which use lasers to determine the distance to the camera. There's also laser sensors that sweep a laser across a scene, and these laser sensors use time of flight to figure out the distance to the sensor. And typically these are one-dimensional signals. They basically sweep in a certain angle and give you this kind of one-dimensional set of values of distances. Now, if we want to get three-dimensional values, we can mount them on a tilt system or a spinning system, and that will allow us to get three-dimensional perception of points in our robot's environment. So sensors vary in their strengths and weaknesses, and there's no perfect sensor. Back in the good old days of the DARPA Grand Challenge, which precipitated a lot of the current work in autonomous vehicles, some of the top teams were using these Velodyne laser sensors that spun around and gave you multiple channels of readings in the vertical axis, but then provided 360-degree view and also very long maximum distance readings. These gave 1.3 million readings per second, and they also came with the downside of a very hefty price tag of $75,000 each. Now, fast forward to today, we can buy, for example, the Intel RealSense L515. This uses lasers to provide a depth image at 30 frames per second, as well as RGB color. And you can get 23 million readings per second at the cost of $350. Now, this has some disadvantages in terms of its maximum range being much shorter. I think it's approximately 8 meters. But in terms of manipulation, this gives us very rich depth readings and very dense reconstructions of 3D worlds that are kind of in a kind of robot manipulation scale. Okay, so let's think about how to deal with images and work with images. Basically, we'll be looking at basic camera modeling. So In general, to get light into a camera, light bounces off some object. It goes through the lens of the camera and then lands on some CCD pixel. This pixel will be on some plane called the image plane. There are various issues regarding lensing that need to be taken into account, such as the depth of focus, illumination, aperture, etc. But for many cameras, these are essentially automatically adjusted for whatever type of application is being addressed. If you're into photography, you'll look much more deeply into these the lensing topics. For the most part, in robotics, we tend to have very small cameras with very small lenses, and these tend not to be so much of an issue. One thing that may be interesting to you is that cameras don't directly sense colors. They actually just sense light intensity. And in order to get color out of your imaging sensor, we use filters such as the Bayer filter, which takes basically a grid of red, green, and blue filters to only let certain wavelengths of light through. Now, with the intermediate pixels, we're going to interpolate the full red, green, and blue colors by doing some sort of interpolation between neighboring pixels. So in order to work with image, we have to understand how to deal with addressing of these pixel arrays. We want to think about images as two-dimensional arrays of colored squares, these pixels. We typically work with red, green, and blue representation, although if you're working with, for example, printing, you may also be using like CMYK colors, etc. These are going to be, the light intensities are going to be quantized, typically to 256 possible values, which is also 1 byte. And oftentimes, well, we want to work with what's known as uncompressed images, which is basically a full matrix of images. And many times you have JPEGs, PNG type of file formats, which actually compress the images. Typically, when you load, then you'll decompress them into this kind of array-based format. The array will have some sort of width and height, but these will typically be packed into a contiguous memory buffer containing W times H times C times 2 to the D bits, where C is the number of channels and D is the bit depth. So now, if we're trying to access a given pixel, you have to be aware of the type of pixel access convention that's being used. Oftentimes, we're going to be working with matrix convention, where the pixel ij goes down I rows from the top and j columns from the left, and then we can access the pixel location given that this conversion here, I times W plus J times the size of the pixel. So this is where the pixel starts. The pixel itself will include some number of channels. So for example, this red block over here, 1,6, is going to be red, and so it's going to have 3 bytes. The first byte is going to be 0xFF, which is the maximum value there, 255, and then the green and the blue are both going to be 0. You should also note that sometimes there's different pixel access conventions. So for example, certain conventions use bottom-up representation, where the row actually goes from the bottom to the top, and there's also XY convention, where the first entry goes left to right and the bottom entry goes bottom to top. Now, how does this correspond to stuff in the 3D world? Well, so we need to model how cameras form images, and we typically do so using what's known as idealized projective geometry. If we have an imaging sensor on an imaging plane, some distance away from the focal point of the lens, then we can model the transformation of the light coming from that point through the lens to the image sensor as a projection transform. So through the rule of similar triangles, the image space point xc here, which is basically given as a sort of coordinate on the image plane in terms of real units, but on the image plane, is going to be the distance from the image plane to the focal point times the x-coordinate divided by z. So that's going to give you 1 coordinate, and there's a similar transform in the y dimension. Now, in order to get pixel coordinates, we're going to scale and offset these using the next transform here, which is known as the viewport transform. So given those real points on the image sensor, we're going to then see which one of the pixels on the image sensor actually gets activated by that light ray. So the point xc, yc gets converted to a pixel by a scaling and an offset. So there's an image center, which corresponds to the 0, 0, direct forward direction of our camera. And there's also going to be a scaling that has to do with the image size, as well as the field of view and the length of the image plane. And so essentially the overall transform that gives you the pixel coordinates is going to be some f times x over z plus some offset cx. Now, if you had a point that went outside of the image range, then it's basically not observed. So you also want to sort of clip things to the inside of this viewport. Okay, so we oftentimes want to do the reverse of image formation. We want to figure out what point in the world generated this pixel that we see. So if we have a pixel coordinate xy, then we can convert to the camera coordinates if we assume that the image plane was at 1 unit away from our focal point. And then we can figure out the world space line through that point, which means that given the x pixel, y pixel, we can convert it to the xyz of that target point. And then any point along that ray between the focal point and that computed point, X camera, Y camera, Z camera, any point along that ray is going to potentially be the generator of that pixel. So there's a bit of redundancy here. If I see something at a certain distance, something in exactly that ray but twice the distance with the same light intensity will generate the same light intensity on my eye. And so this is a subject of a lot of possible, for example, optical illusions that play with your sense of scale and depth estimation. Now, we oftentimes we don't just want to go from pixels to points in the space, but we also want to recognize objects in the scene. And we'll talk about this when we get into computer vision. So there's lots of different types of computer vision algorithms, ranging from classical image processing to feature detection algorithms, segmentation algorithms, as well as deep learning approaches. And so we'll get into this in a future lecture. The really tricky part about computer vision is that appearance really changes greatly depending on the viewpoint and the lighting conditions. So for example, this slightly overhead view of the White House that's taken from fairly far away is very different from the image that we see on the right here. So you can see that in the first image, it takes up a tiny part of the image. There's also a fairly large distance between the pool in the front and the building itself. But if we see a image taken from the ground, this square is taking up a much larger part of the image. The pool is taking up a huge part of the foreground. It's even sort of blocked and you can't even see the water from here. But if you want to, for example, be really reliable at recognizing an object, you have to be able to develop algorithms that will be tolerant to these changes of the viewpoint as well as lighting conditions. There's other issues that we have to deal with real sensors, especially when we're dealing with images taken from robots, because oftentimes when we're talking about computer vision, you're oftentimes taking pictures that people have selected based off of photographic intuition. And so we'll oftentimes toss out images that have poor exposure or motion blur, etc. But we can't control this so well on our robots. And so here we have to worry about these types of things and develop algorithms somewhat specifically for robots if we're going to make them reliable, especially for example, moving robots or robots that need to work with very different lighting conditions. A couple of other tasks that are used. So for example, stereo vision processing is trying to construct a three-dimensional representation of the world given two sensors. So if we take two images that are slightly offset from one another, these are called, the offset between them is called the baseline of the stereo pair. If we see the same object from each of these cameras, there's going to be an apparent offset in the horizontal direction that's known as the binocular disparity. So you can test this out by putting your finger in front of your eye, closing one eye, and then switching to the other one. You can see your finger switching in apparent position from left to right, and vice versa. So the idea is that if we can recognize some part of the image on one image, usually taking the left image into account as the reference, and then find the same patch in the right image, then we can try to search for how much that has been shifted. And then this corresponds to the depth by an inverse transform. So the less binocular disparity you get, the farther the object is away. Now, there's a lot of different complexities in terms of building dense reconstructions, in terms of the algorithms for performing matching, etc. But there's a couple of aspects of stereo vision that are very common. One is that they perform much better in textured scenes than in untextured scenes. So if you looked at a wall, for example, that was completely blank, stereo vision would do very poorly because it can't find good matches. Now, if you see a highly textured scene like this, there's a lot of good matches, and so you get fairly good reconstructions. Another type of technique that is operating on a similar principle is called structured light. This became very popular with the Microsoft Kinect and now more recently the Intel RealSense line of cameras. Here they provide dense 3D depth estimates in color. They have a color sensor as well as an IR infrared depth sensor and an infrared emitter. So the emitter generates synthetic texture on the scene, which allows the binocular disparity to be estimated more accurately. Now there's a baseline between the IR emitter and the IR depth sensor. The depth sensor knows what was emitted. There's some pattern that gets emitted onto the scene, such as the one shown here. And by doing a binocular reconstruction, a dense reconstruction, you can get fairly good estimates of depth for scenes that are not too washed out. Now, if there's bright light, then the readings that you get back are going to be dominated by the bright light rather than the pattern that's emitted by this IR emitter, and so you end up getting poor performance outdoors. Now, if you have a set of depths, so depth here is actually going to be not exactly the distance from the camera, but rather the distance in the forward direction only of the camera. With this measurement, we can figure out from a pixel coordinate and the depth at that pixel coordinate, we can figure out the world space line through that pixel, but we know the depth, we know the z value given from the sensor, and so we can just reconstruct the x, y, and z from that point through this following transform shown here. Now with this, we get what's known as a point cloud. So a point cloud is basically it's a list of points in 3D space. Each point can have color, some sort of sensor reading ID, and surface normal. As we've said before, these don't have information about which objects are in the scene, the occlusions, or the topology, but in any case, these are very rich representations which are very useful for doing manipulation planning especially. A couple of characteristics about point clouds that we have to worry about. So the biggest one is occlusions. We oftentimes don't see a lot of there's a lot of missing data, especially these sorts of shadows. So we basically see the front sides of objects, we don't see the backs, we don't see what's behind them. There's also oftentimes limited range depending on the type of sensor that you have. They'll also miss small features due to the resolution. So if we're trying to pick up a very small object, they may be sub-pixel size in the frame of the image. And in that case, we'll likely miss them. They also have non-uniform coverage of the 3D scene, so objects that are farther away will have a sparser sampling in terms of points per unit area compared to objects that are close to the sensor. And there's also going to be a lot of noise in these images, and they're typically proportional to depth, and so you'll oftentimes see characteristics like 1% depth measurement error, 2% depth measurement error, meaning that if you are at 1 meter away, then you're expecting to see, for example, 1 centimeter of error in the depth. There's also systematic errors, including these occlusions, exposure, various calibration errors, and reflective surfaces. So oftentimes you'll get bogus readings or no readings from these types of sensors, these point clouds. So we have to be a bit wary of how to deal with these types of systematic errors in our data. So one very important one is stereo occlusions, because many times these point clouds are generated through stereo reconstruction. Again, because of stereo disparity, the points that you can see in one camera image are not going to be exactly the same as the points you can see in the other camera image. So if we look at these two images of this water bottle and this keyboard in the back, there's parts of the keyboard that are not seen in the left image. There's also parts of behind both behind the bottle as well as those on the extreme side of the image. So these points can't be reconstructed in our stereo image. There's also going to be problems registering the color information to the depth information, particularly for these structured light cameras, because there's an infrared camera, a color camera, and an infrared emitter, all of which are not exactly co-located on the same focal point. So you'll tend to see color bleeding of objects that are in front of some kind of background, and the color of the object in the foreground will oftentimes bleed over to the color of the points in the background. Another very common type of artifact is outliers, and so it's oftentimes very important to do outlier rejection. So the idea is that there's some sort of signal of objects that actually exist. The noise is going to be perceived as sort of, points out in the middle of space. So for point clouds, we can oftentimes use the fact that spurious noise is distributed in a less dense region of space than points that are actually corresponding to objects. And so we can use various types of outlier rejection techniques or simple criteria to reject these outliers and hopefully just get the objects that actually exist in the real world. Okay, so just as a recap, this is a kind of a brief introduction of perception versus sensing, working with images, dealing with projective geometry and 3D vision. We just barely scratched the surface of the phenomenon of real sensors, and if you're going to be studying this topic in more depth, this whole field is an art about how you deal with these real phenomena. That's it for this time. We'll talk much more about these types of approaches in future